What if the numbers we use to measure every hour of our lives, every degree of every circle, every coordinate on every map, didn't come from gradual human discovery, but from something else entirely? What if the mathematics that built our world arrived fully formed in the hands of people who had no business possessing it, pressed into clay tablets by scribes who copied formulas they may not have fully understood, preserving calculations that wouldn't be matched again for 3,000 years? In the basement archives of Columbia University, behind glass and climate control, rests a small clay tablet no larger than a smartphone. Its surface is covered in wedge-shaped marks arranged in neat columns and rows. The catalogue calls it Plimpton 322, named after the collector who donated it in 1936. For decades, scholars assumed it was a merchant's account ledger, another bureaucratic record from ancient Mesopotamia's endless clay libraries. Then in 1945, a mathematician looked closer at the numbers and realised what he was seeing. The tablet contained a trigonometric table more accurate than anything that would appear again until the Greeks, 15 centuries later. But here's what made it impossible. The Sumerians, who created it around 1800 BCE, had no concept of trigonometry as we understand it. They had no Pythagoras, no geometry textbooks, no centuries of mathematical evolution leading to this level of sophistication. The knowledge was just there, complete and functional, as if someone had handed them the answer key before they'd even learned to ask the questions. Before we go further, if you're drawn to stories where ancient precision feels more like inheritance than invention, consider subscribing. And if you're listening somewhere in the quiet hours, drop a comment telling me where you are and what time it is where the night finds you. I want to imagine this mystery unfolding across time zones, carried into sleep by people who wonder if we've been reading history backward. The tablet is cool when the archivists handle it with cotton gloves, slightly rough along the edges where time and handling have worn it smooth. Each cuneiform mark was pressed deliberately into wet clay by a reed stylus held in a hand that hasn't existed for nearly 4,000 years. And if you could examine it closely enough, you'd see them still. The faint impressions of fingertips preserved in the hardened mud, the pulse of a scribe who believed this knowledge mattered enough to survive. That scribe was working in the city of Larsa in southern Mesopotamia, in a scribal school where students learned to calculate areas, compound interest, square roots, and celestial movements. They were using a mathematical system so sophisticated that we still haven't fully abandoned it. Every time you read a clock, you're using Sumerian math. Every time you navigate by degrees, you're thinking in their numbers. 60 seconds in a minute, 60 minutes in an hour, 360 degrees in a circle. The system is called sexagesimal, base 60. And it came from Sumer fully formed with no evolutionary trail leading backward to simpler methods. This should be impossible. Mathematical systems don't appear complete, they evolve. The Egyptians developed their mathematics gradually over centuries, starting with simple counting and slowly building toward fractions and geometry. You can trace their progress through increasingly complex papyri, watching as they solve harder problems, make mistakes, develop shortcuts, refine techniques. The same pattern holds in China, in India, in Greece. Math grows, it accumulates. One generation solves a problem, the next builds on that solution, and slowly, across lifetimes, complexity emerges. But not in Sumer. When cuneiform tablets first appear in the archaeological record, around 3200 BCE. The earliest ones already contain multiplication tables, division algorithms, and geometric calculations. There are no primitive stages, no awkward first attempts, no centuries of trial and error preserved in clay. The Sumerians begin their written record already fluent in advanced mathematics, as if they were documenting a system someone had already taught them. In the 1930s, archaeologists working in the ruins of Nippur, Sumer's religious centre, unearthed a room filled with thousands of clay tablets. They expected religious texts, hymns to forgotten gods, records of temple offerings. What they found instead was a Scribal school's math homework, tablets covered in multiplication tables, practice problems calculating areas of irregular fields, word problems about workers digging canals and distributing rations, advanced exercises involving cube roots, and exponential growth. The students who worked these problems were learning math we wouldn't teach again until high school algebra, and they were doing it 3,800 years ago using a number system that somehow encoded more elegance than our modern base 10. The sexagesimal system isn't arbitrary. It's mathematically optimal for a pre-calculator world. 60 is the smallest number divisible by 1, 2, 3, 4, 5 and 6. This makes fractions simpler. Divide 60 by 2, you get 30, by 3, 20, by 4, 15, by 5, 12, by 6, 10. Every division produces a whole number, no messy decimals, no rounding errors. For a civilization doing complex calculations by hand, this system was a gift. But here's the question no one has satisfactorily answered. How did they discover it? If you wanted to develop base 60 through experimentation, you'd need to test different number systems, compare their efficiency, recognise the unique divisibility advantages of 60 over 59 or 61, and then convince an entire civilization to adopt your conclusions. This process should take generations and leave behind evidence of competing systems, failed experiments, and gradual adoption. None of that exists in the Sumerian record. Base 60 appears complete in the earliest mathematical tablets we found, already standardized across multiple cities, as if it had been taught rather than invented. And it's not just the system itself, it's what they did with it. Plimpton 322, that small tablet in Columbia's archive, contains what we now recognise as Pythagorean triples, sets of three numbers that satisfy the equation a squared plus b squared equals c squared, the foundation of right-angle geometry. The tablet lists 15 of these triples arranged in descending order of a specific trigonometric ratio. Whoever created it understood geometric relationships we attribute to Pythagoras, who wouldn't be born for another 1,200 years. They understood them so well, they could generate tables of values, not through lucky guessing, but through systematic calculation. When mathematician Otto Neugebauer first analysed Plimpton 322 in detail, he realised the scribe had made small errors in a few entries. Not conceptual errors, but copying mistakes. Numbers transposed or digits dropped. This told him something crucial. The tablet wasn't an original creation. It was a copy. Someone, somewhere, had compiled the original table, and scribes had been copying it for so long that small errors had crept in through generations of transcription, which means the knowledge encoded in Plimpton 322 was already old when it was pressed into clay, already being preserved, already being passed down, already treated as inherited wisdom rather than fresh discovery. The scribes copying these tables might not have even fully understood what they were preserving. They were simply maintaining accuracy, carrying forward the numbers because the numbers mattered, because someone long ago had decided this knowledge must survive. In a climate-controlled room in the British Museum, another tablet rests in archival storage. Catalogue number B, M13901, dated to roughly the same period as Plimpton 322. This one contains a geometric problem about a square and its diagonals. solved using what we now call the square root of 2. The scribe calculated it to 6 decimal places. Let that settle for a moment. 6 decimal places. That level of precision wouldn't appear again in Western mathematics until the 16th century, 3,000 years later. The tablet doesn't show the work, doesn't explain how the scribe arrived at such accuracy. It simply states the value as if everyone already knew it, as if the square root of 2 to 6 places was common knowledge in Sumerian scribal schools, obvious and unremarkable. How? How does a civilization with no computers, no symbolic algebra, no place-value decimal system achieve computational precision that we associate with modern engineering? And why does that precision appear complete from the beginning, with no trace of the centuries of mathematical development that should precede it? Some scholars argue we simply haven't found the earlier stages yet, that erosion and time have destroyed the tablets showing Sumer's mathematical childhood. But thousands of tablets have survived, tens of thousands. They cover every aspect of daily life, from beer rations to property disputes, to astronomical observations. If there were centuries of primitive mathematics, we should see them. We should find tablets with mistakes, with competing number systems, with arguments about which method works best. Instead, we find consistency, a mathematical language already perfected, already standardized, already being copied and preserved as if it was sacred text. Others suggest the Sumerians inherited their mathematics from the Ubaid culture that preceded them in the same region, but the Ubaid left behind simple farming villages with basic pottery and stone tools, no monumental architecture, no writing, no evidence of mathematical sophistication. Then Sumer appears, and suddenly there are scribal schools teaching calculus of compound interest, geometric progressions, and astronomical calculations that track planetary movements. The gap is too wide, the leap too sudden. It feels less like evolution and more like transplantation, as if someone placed advanced knowledge into the hands of people just learning to write it down. And there's one more detail that haunts every analysis of Sumerian mathematics. The system was never improved. For 1500 years, from roughly 3200 BCE until Sumer was absorbed by Babylon around 1750 BCE, the sexagesimal system remained unchanged. No innovations, no refinements, no mathematical revolutions. The same tables were copied, the same methods applied, the same precision maintained. It was perfect at the beginning, and it stayed perfect until the civilization that used it faded into history, leaving behind clay fragments that whisper of knowledge we still struggle to explain. Somewhere in the ruins of ancient Uruk, buried beneath layers of sand and collapsed architecture, more tablets wait. Thousands more, still unexcavated, still silent. And each one might contain another impossibility, another calculation that shouldn't exist, another formula pressed into clay by hands that somehow knew things we've spent millennia relearning. Maybe that's why these tablets feel different when you study them. They don't read like discovery, they read like documentation. Not, look what we figured out, but here's what we were taught. Preservation, not innovation. Memory, not invention. As if the Sumerians were archivists of someone else's mathematics, copying and maintaining knowledge whose origins they themselves may not have fully understood. But if that's true, if Sumerian math came from an unknown source, then the next question pulls us somewhere darker. Who taught them? And why did the teaching stop? The discovery didn't happen in dramatic fashion. It happened with dust and patience, in the summer heat of Iraq, where temperatures climb past 120 degrees, and the ruins shimmer like mirages against the horizon. In 1854, British archaeologist Henry Rawlinson was excavating near the ancient city of Sippar when his team uncovered a room filled with clay tablets stacked in organised rows. They had been deliberately preserved, arranged by subject matter, catalogued by scribes who understood they were maintaining a library. When the tablets were cleaned and translated, Rawlinson realised he wasn't looking at religious texts or royal propaganda. He was looking at math curriculum, textbooks from a scribal school nearly 4,000 years old, still teaching students how to calculate compound interest and solve quadratic equations. One tablet, now housed in the British Museum, contains a problem that stops modern mathematicians cold. It describes a rectangle with given area and diagonal length, then asks the student to calculate the sides. The solution requires manipulating what we now call quadratic equations, equations where the unknown value is squared. The Sumerian scribe solves it correctly, using a method identical to the one we teach in algebra classes today. But here's what fractures our understanding of mathematical history. Quadratic equations weren't supposed to exist until the Babylonians refined them around 1600 BCE. Then the Greeks systematized them centuries later. Then Islamic scholars perfected them in the medieval period. And finally, European mathematicians gave them the symbolic notation we use now. That's the story we tell about the development of algebra, a slow accumulation of techniques across cultures and centuries. Except the Sumerians were already solving these problems 1,000 years before the Babylonians, using methods that show no primitive groping toward understanding. The solutions are clean, efficient, systematic. Not the work of people discovering algebra for the first time, but the work of people applying established procedures they'd been taught. Compare this to how mathematics actually develops in cultures we can fully document. In ancient Egypt, we have the Rhind mathematical papyrus from around 1550 BCE, which contains 84 problems ranging from simple arithmetic to complex geometry. You can watch Egyptian mathematics evolve through earlier papyri, seeing how they struggled with fractions, developed awkward but functional methods, made conceptual leaps, hit dead ends, and slowly refined their techniques. Problem 19 in the Rhind papyrus asks how to divide 9 loaves of bread among 10 men. The Egyptian solution is cumbersome, breaking the problem into unit fractions and manipulating them through multiple steps to reach an answer. It works, but it's clumsy. You can feel the mathematical system straining, not quite equipped for the task, forcing the scribe to work around its limitations. That's what early mathematics looks like. Functional but awkward, solving problems despite the tools rather than because of them. Sumerian mathematics doesn't feel like that. When a Sumerian tablet asks how to divide a number, the scribe uses place value notation and divisibility rules built into the base 60 system to arrive at answers with minimal effort. The mathematics flows. The tools match the problems perfectly, as if the system had been designed by someone who already knew what kinds of calculations would be needed and built the framework to handle them elegantly. And it's not just algebra. Tablets from excavated by Leonard Woolley in the 1920s, contain geometric calculations for irregular field shapes, problems that require understanding area, ratios, and approximations. One tablet calculates the area of a trapezoidal field using a formula that wouldn't be formally proven until Euclid wrote his Elements around 300 BCE, 2,000 years later. The Sumerian scribe doesn't explain the formula, doesn't justify why it works. They simply apply it as if everyone knows this is how you calculate trapezoidal areas, obvious and settled knowledge. In China, we can trace mathematical development through the 9 chapters on the mathematical art, compiled around 100 BCE but drawing from earlier sources. The text shows Chinese mathematics evolving through practical problems, merchants calculating prices, builders measuring materials, tax collectors assessing land. Early methods are rough approximations that gradually become more precise as techniques improve. Chapter 4 deals with finding square roots, and you can see the authors working through different approaches, some more accurate than others, refining their method across multiple problems. That's the signature of indigenous mathematical development. Visible progress from crude to sophisticated, documented in the very texts that teach the methods. Where is this progression in Sumer? Where are the tablets showing scribes figuring out how to calculate square roots for the first time, testing different approaches, making errors, correcting themselves? They should exist. Mathematics isn't born perfect. It's refined through use, through failure, through generations of practitioners encountering new problems that force innovation. But the Sumerian tablets present mathematics as already refined, already tested, already proven reliable. In the Louvre, tablet AO 6484 cites, in a glass case, in the ancient Near East collection. It contains a problem about a circular granary, calculating how much grain it can hold based on its diameter and height. The solution uses an approximation of pi, the ratio of a circle's circumference to its diameter, calculated as 3.125. That's remarkably close to pi's true value of 3.14159. The scribe doesn't explain how they arrived at this approximation. They don't show the measurements or experiments that would let someone derive it empirically. They simply use it, as if the value of pi were common knowledge, filed away in every scribe's mental library, alongside multiplication tables and conversion factors. How did they know? Pi isn't an obvious number. You can't count to it. You have to discover it through careful measurement of circles, comparing circumferences to diameters, averaging results, recognizing the pattern. That process should leave traces, tablets showing the experimental work, the measurements, the gradual refinement toward accuracy. None of that exists in the Sumerian record. Pi simply appears, already approximated to useful precision, already being applied to practical problems. Perhaps even stranger is what happens with Sumerian mathematics after Sumer falls. When Babylon rises to power around 1900 BCE, absorbing the Sumerian territories and culture, Babylonian scribes inherit the sexagesimal system. They use it, they maintain it, they copy the old Sumerian tablets and create new mathematical texts using the same base 60 framework, but they don't improve it. For another 1,000 years, through the rise and fall of Babylon, through the Kassite period, through the Neo-Babylonian Empire, the mathematics remains essentially unchanged. New problems are solved using old methods. The same tables are copied with the same values. The same precision is maintained. It's as if the system were complete, leaving no room for innovation because there was nothing left to innovate. Every tool needed for ancient computation already existed in the framework the Sumerians had left behind, perfect and unchanging. Contrast this with the explosive development of mathematics in other periods of history. When the Greeks encountered Babylonian astronomy and mathematics through conquest and trade, they revolutionized it within a few generations. Thales, Pythagoras, Euclid, Archimedes, each building on the previous, each pushing mathematics into new territories, creating proofs and abstractions and theoretical frameworks that transform numbers from practical tools into philosophical objects. That's what happens when mathematically inclined minds encounter a functional system. They question it, expand it, test its limits, search for deeper principles. The Sumerians and their Babylonian inheritors did none of this. They preserved, copied, maintained, but never fundamentally changed the mathematics they'd inherited. As if they understood they were caretakers of something they hadn't created, custodians of knowledge whose origins they themselves might not have fully understood. Imagine holding one of these tablets now, the weight of it in your hands, the rough texture of fired clay that survived, because fire preserves rather than destroys. Run your fingers over the cuneiform marks, feeling the slight indentations where a stylus pressed into wet mud nearly 4,000 years ago. The person who made those marks was solving a mathematical problem that wouldn't be formally taught in Europe until the Renaissance. They were doing it without symbolic algebra, without place-value decimals, without calculators or computers, using only a reed stylus and a system they'd inherited from teachers who had inherited it from teachers who had inherited it from someone, somewhere, whose name is lost to time, but whose mathematics survived, perfect and complete, pressed into clay that would outlast empires. In the silent archives where these tablets rest, behind climate control and security glass, they wait like coded messages from a world that understood things we've spent millennia relearning, and the questions they pose are more unsettling than any answers we found. How does a civilization develop perfect mathematics with no evolutionary history? How do they calculate to 6 decimal places without the notation that makes such precision manageable? How do they solve quadratic equations 1,000 years before algebra is supposed to exist? And why, if they were capable of such mathematical sophistication, did they never push beyond it, never innovate, never revolutionize their own system? Unless they couldn't, unless they were preserving rather than creating, maintaining knowledge they'd received rather than discovered, carrying forward calculations taught to them by someone whose identity has dissolved into myth, and whose mathematics remains precise and inexplicable, the legacy of an unknown source. But Sumer wasn't alone. That's what makes this pattern impossible to dismiss as coincidence or scholarly misinterpretation. When you expand the lens beyond Mesopotamia, when you look at what other ancient cultures were doing with numbers and time and celestial observation, the same fingerprints appear. Not identical systems, but the same underlying sophistication arriving without precedent, the same base 60 mathematics woven into the fabric of civilizations that should have had no contact with Sumer, separated by thousands of miles and centuries of history. The pattern repeats with such consistency that it stops feeling like independent invention and starts feeling like shared inheritance, as if multiple cultures were drawing from the same deep well of knowledge, preserving fragments of something older than any of them. In the winter of 1939, archaeologist Wilhelm König was cataloguing artifacts in the basement of the National Museum of Iraq when he noticed something strange about a small clay jar from the Parthian period, roughly 200 BCE. Inside the jar was a copper cylinder, and inside that cylinder was an iron rod held in place with asphalt. The components were corroded but intact, and when König examined the construction, he realized what he might be looking at. The jar, if filled with an acidic liquid like vinegar or wine, would function as a galvanic cell, a primitive battery capable of generating electrical current. Modern replicas produce about 1.1 volts, enough for electroplating or possibly medical applications. Whether the Baghdad battery, as it came to be called, actually generated electricity is still debated. But here's what isn't debated. The mathematical knowledge required to deliberately create such a device, understanding ratios of metals, calculating appropriate dimensions, predicting chemical reactions, shouldn't exist in 200 BCE Mesopotamia. Yet if the object is what it appears to be, someone possessed that knowledge, applied it practically, then lost it so completely that electrical generation wouldn't be rediscovered until Alessandro Volta in 1800 CE, 2,000 years later. Move west to Egypt, where the Great Pyramid of Giza rises from the desert plateau with a precision that still troubles engineers. Built around 2560 BCE, the pyramid's base is level to within 2.1 centimetres across a span of 230 metres. Its sides are aligned to true north, with an error of less than 3 arc minutes, 1/20th of 1 degree. Achieving this precision with copper tools and wooden measuring rods requires mathematical knowledge far beyond what we attribute to 3rd Dynasty Egypt. The pyramid's dimensions encode sophisticated geometric relationships. Its height multiplied by 2 times pi equals the perimeter of its base, meaning the structure incorporates the golden ratio and an accurate value of pi into its fundamental design. The builders would have needed to calculate pi to at least 3.14, the same level of precision the Sumerians used in their granary calculations, and they would have needed to maintain that precision across millions of limestone blocks, each cut and placed with minimal deviation. Where did they learn this? Egyptian mathematical papyri from the same period show a civilization still struggling with basic fractions, still using awkward methods to divide numbers. Yet somehow they built a structure whose mathematical elegance wouldn't be fully understood until modern surveying equipment could measure it accurately. The architect of the Great Pyramid, according to Egyptian records, was Imhotep, high priest and vizier to Pharaoh Djoser. Later generations would deify him as a god of wisdom and medicine, suggesting his knowledge seemed supernatural even to ancient Egyptians. Temple inscriptions describe him as possessing wisdom from before, knowledge inherited rather than discovered. The language echoes what we find in Sumerian texts, this recurring theme of restoration and preservation, of building not from innovation but from memory. And like the Sumerians, Egyptian mathematics doesn't evolve much after its initial appearance. It maintains, it preserves, it applies established methods to new problems, but it doesn't revolutionize itself. The same techniques used in the age of the pyramids are still being used 1,000 years later, copied and recopied, passed from master to student, with reverence for accuracy rather than enthusiasm for innovation. Cross the globe to Mesoamerica, where the Maya developed a mathematical system completely independent of Old World influence, or so the standard narrative tells us. Mayan mathematics uses base 20, not base 60, counting on fingers and toes rather than some other principle. But look closer at what they achieved with it. Mayan astronomers calculated the length of the solar year as 365.242 days. Modern astronomy, using atomic clocks and satellite measurements, puts it at 365.2422 days. The Maya were off by 2 ten-thousandths of a day, an error so small it accumulates to less than 1 full day over 5,000 years. They calculated the lunar month as 29.53059 days. We measure it as 29.530588 days. The difference is 7/10 of a day. That level of precision requires generations of continuous observation, mathematical methods for averaging and correcting measurements, and institutional memory that can maintain accuracy across centuries. Yet, when Spanish conquistadors arrived in the 16th century, they found these calculations recorded in bark paper codices using a mathematical system that showed no evolutionary development, no earlier crude attempts, no progression from simple to sophisticated. Mayan mathematics appears in the archaeological record already capable of astronomical calculations that rival modern precision, as if the system had been designed specifically for tracking celestial movements by someone who already understood the sky perfectly. And here's what connects the Maya to Sumer across 6,000 miles and 2,000 years. Both cultures were obsessed with the same astronomical period. The Sumerians tracked what they called the Sar cycle, 3,600 years, a period that shows up repeatedly in their king lists and astronomical texts. The Maya calculated what they called the long count, a calendrical system that measures time in cycles of 5,125 years, with smaller units called baktuns of 394 years. These numbers aren't arbitrary. They're derived from careful observation of planetary conjunctions, the points where multiple celestial bodies align in ways that repeat over vast timescales. The Sumerians calculated that Venus completes a full cycle and returns to the same position relative to Earth and the Sun every 3,240 years, 8 Venus years or 5 Earth years. The Maya tracked the same Venus cycle with equal precision, encoding it into their calendar system, building temples aligned to Venus rising, organising their ritual life around a planet whose movements they understood with mathematical exactness. Two cultures, no contact, same obsession, same precision. Independent invention should produce variation. This is replication. In the ruins of Chichen Itza, the pyramid called El Castillo demonstrates this obsession with astronomical mathematics. Built around 1000 CE, the structure has 91 steps on each of its 4 sides, totaling 364 steps, plus the platform at the top makes 365, one for each day of the solar year. But it's not just symbolic. During the spring and autumn equinoxes, the angle of the sun creates a shadow pattern on the pyramid's northern staircase that looks exactly like a serpent descending from the sky, 7 triangles of light forming the body, the carved serpent head at the base forming the point where the celestial snake touches the earth. Creating this effect requires calculating sun angles, understanding the geometry of shadows, positioning the staircase at exactly the right orientation, and carving the stone with precision that allows light and shadow to align only on those 2 specific days. The mathematics required to design this aren't simple. They involve trigonometry, solar declination tables, and geometric projection, skills we associate with Renaissance astronomy, being applied by Mayan architects who are supposedly working with stone tools and no written mathematical treatises beyond what we've found in their few surviving codices. Meanwhile in India, the Surya Siddhanta, an ancient Sanskrit text on astronomy whose origins are debated but likely predate 400 CE, contains calculations of planetary diameters, distances, and orbital periods that match modern values with shocking accuracy. The text calculates Earth's diameter as 8,000 miles. We measure it as 7,917 miles. Close enough that the ancient calculation feels less like lucky guessing and more like preserved measurement. The text uses a value for pi of 3.1416, accurate to 4 decimal places, and applies it to calculate celestial movements, eclipse predictions, and the precession of the equinoxes. That last calculation is particularly troubling. Precession, the slow wobble of Earth's axis that causes the position of stars to shift over millennia, takes 25,772 years to complete one full cycle. The Surya Siddhanta gives a value of 24,000 years, close enough to suggest the authors understood precession existed and had observed it long enough to calculate its period, something that requires continuous astronomical observation over thousands of years, institutional memory spanning generations, and mathematical sophistication to translate raw observations into theoretical understanding. The Greek astronomer Hipparchus is credited with discovering precession around 130 BCE, making careful observations and comparing them to Babylonian star charts from centuries earlier. His calculation was off by several thousand years because even with Babylonian records, he didn't have enough temporal baseline to measure a phenomenon that unfolds so slowly. Yet somehow the authors of the Surya Siddhanta, working in India with no confirmed access to Babylonian data, calculated precession with better accuracy. Where did their data come from? How many centuries of continuous observation would be required to recognise that the stars were shifting position relative to the equinoxes? And why does this knowledge appear in a text that shows no progression, no record of the centuries of observation that should underpin its conclusions? It presents its calculations as established fact, inherited wisdom, knowledge passed down from earlier sources the text vaguely attributes to divine revelation. Notice the pattern. Sumer, Egypt, Maya, India, 4 civilizations separated by geography and time, all demonstrating mathematical and astronomical sophistication that appears complete without developmental stages, all encoding the same obsessions, tracking the same celestial cycles, using compatible mathematical frameworks to describe the movements of planets and stars, all preserving rather than innovating, maintaining systems they inherited from sources they describe in mythological terms but treat as historically real. The Maya speak of teachers from across the sea who brought knowledge after the world was destroyed by flood. The Sumerians speak of the Anunnaki who descended from heaven to establish civilization. The Egyptians speak of the followers of Horus, divine beings who ruled before the pharaohs and taught humanity the arts of building and measuring. The Indians speak of the Saptarishi, 7 sages who preserved knowledge through cycles of cosmic destruction and recreated civilization in each new age. Different names, different mythologies, same narrative structure. Knowledge comes from elsewhere, from before, from beings who possessed wisdom and passed it to humans who then became responsible for maintaining it. If these were isolated stories, we could dismiss them as cultural mythology, the universal human tendency to attribute innovation to divine intervention. But when the mythology is accompanied by actual mathematical and astronomical achievement that matches the myths, when cultures really do possess knowledge they shouldn't have according to our developmental models, when that knowledge really does appear complete and unchanging, rather than evolutionary, then maybe the myths deserve closer attention. Maybe they're not explaining where knowledge comes from in some abstract cosmic sense. Maybe they're documenting where specific mathematical and astronomical systems came from, encoding the memory of teaching in the only narrative framework available to pre-literate or early literate cultures. Not gods in the theological sense, but teachers in the historical sense, people or groups who possessed advanced knowledge and transmitted it before disappearing into the shadows of prehistory, leaving behind only fragments, formulas pressed into clay, calculations carved into stone, calendars that still work, mathematics that still functions, all of it preserved by civilizations who saw themselves as custodians rather than creators. And if that's true, then the question becomes inescapable and unsettling. Where did the teachers learn? There's a layer of sediment that appears in geological cores taken from sites across the northern hemisphere, dated to roughly 11,600 years ago. Geologists call it the Younger Dryas boundary layer, and it marks one of the most dramatic climate shifts in recent Earth history. Within a span of perhaps 10 to 20 years, temperatures plummeted. Ice sheets that had been retreating suddenly advanced again. Sea levels dropped, then rose catastrophically as ice dams failed and meltwater flooded into the oceans. Entire ecosystems collapsed. Megafauna that had survived hundreds of thousands of years of ice age cycles went extinct within generations, and according to recent evidence, something burned. The boundary layer contains elevated concentrations of platinum. Microscopic diamonds formed under extreme heat and pressure, and widespread deposits of carbon suggesting massive wildfires that consume forests across continents. Something happened at the end of the last ice age, something sudden and catastrophic enough to leave a signature in the geological record that we're still trying to fully understand. Now consider what that event would do to human civilization, if any existed, at the level of sophistication required to develop advanced mathematics and astronomy. Coastal settlements would vanish beneath rising seas. Agricultural centres dependent on stable climate would fail as temperatures shifted. Trade networks would collapse as populations migrated or died. Knowledge would fragment as the institutions that preserved it, scribal schools, astronomical observatories, centres of learning, disappeared beneath water or fire or social chaos. Within a few generations, maybe less, advanced knowledge could reduce to folklore, carried by survivors who no longer understood the full context of what they were preserving, passing down formulas and calculations as sacred tradition because the theoretical framework that explained them had been lost. This is how civilizations forget. Not gradually, but catastrophically, when the infrastructure that maintains knowledge is destroyed faster than it can be transmitted. Plato wrote about this in the Timaeus, one of his later dialogues composed around 360 BCE. He describes a conversation between Solon, the Athenian lawmaker, and Egyptian priests at Sais. The priest tells Solon that Greek civilization is young, that Greeks have no ancient traditions because their history is repeatedly destroyed by catastrophe. They speak of periodic destructions, some by fire, some by flood, that wipe out all but scattered survivors who have to rebuild from nothing, losing their writing, their arts, their history. The priests claim Egypt preserves older memories because the Nile's geography protects it from the worst floods, allowing institutional continuity across catastrophes that devastate other regions. Then they tell Solon about Atlantis, a powerful civilization that existed 9,000 years before their conversation, destroyed in a single day and night of catastrophic flooding. Modern scholars dismiss Atlantis as Plato's philosophical fiction, an invented society used to explore ideas about ideal government and moral decline. But embedded in the story are details that feel less like invention and more like garbled memory. Plato describes Atlantis as possessing advanced engineering, sophisticated mathematics, astronomical knowledge, and a civilization-wide obsession with circles and geometric precision. The capital city is arranged in concentric rings of water and land, ratios and proportions carefully maintained, the whole structure a physical embodiment of mathematical harmony. Whether Atlantis existed doesn't matter as much as what the story preserves. The idea that advanced civilizations can exist and be destroyed so completely that only fragments survive, transmitted through cultures that no longer understand what they're describing, encoded in mythology because history has been erased. And here's what makes the Atlantis story relevant to Sumerian mathematics. Plato claims the priests dated Atlantis' destruction to approximately 9,000 years before Solon's visit, which would place it around 9600 BCE. The Younger Dryas impact hypothesis suggests major catastrophe around 10,800 BCE, close enough that some researchers wonder if Plato's date preserves genuine chronological memory, passed through Egyptian records, referencing a real event whose details were mythologized but whose timing was maintained. If a civilization sophisticated enough to develop base 60 mathematics and precise astronomy existed before the Younger Dryas catastrophe, and if that civilization was largely destroyed, leaving only scattered survivors and fragments of knowledge, then what we see in Sumer starts to make sense. Not a civilization inventing mathematics, but a civilization inheriting it, receiving fragmentary instruction from survivors or descendants of survivors who carried formulas and methods they'd learned before the world changed, teaching them to new cultures emerging in the post-catastrophe world, passing them down with such reverence that they were preserved unchanged for thousands of years, copied and maintained as sacred knowledge whose origins had faded into myth. This would explain why Sumerian mathematics appears complete. It wasn't developed in Sumer. It was received, already refined through centuries or millennia of use in the lost source civilization, then transmitted to Sumer in a form that was functional but perhaps not fully understood. The Sumerian scribes became preservers of someone else's mathematics, maintaining accuracy through careful copying, treating the knowledge as too important to alter, which is why we see no innovation, no mathematical revolutions, just faithful preservation across 15 centuries until Sumer itself faded and Babylon inherited the same tables, the same methods, the same base 60 system, carrying it forward for another 1,000 years. And it would explain the global pattern, why similar mathematical and astronomical sophistication appears in Egypt and India and Mesoamerica without clear developmental stages. If the source civilization had global reach, or if multiple survivor groups scattered to different regions after the catastrophe, they could have carried the same knowledge to different populations, adapting it to local conditions but maintaining the core framework, which is why we see base 60 in Mesopotamia and base 20 in Mesoamerica, but the same astronomical obsessions, the same precise calculations, the same encoded understanding of planetary cycles and geometric relationships. Is there evidence for a sophisticated pre-Younger Dryas civilization? Not the kind archaeologists prefer. Not cities and roads and monumental architecture surviving intact across 12,000 years of geological activity. But there are anomalies, sites that predate established timelines and demonstrate capabilities that shouldn't exist in their periods. Göbekli Tepe in southern Turkey, dated to 9600 BCE, consists of massive stone pillars arranged in circles, carved with sophisticated reliefs of animals and abstract symbols, erected by people who supposedly hadn't yet developed agriculture or permanent settlements. The site required organising hundreds of workers, quarrying and transporting stones weighing multiple tons, planning and executing architectural designs of considerable complexity, all before civilization is supposed to exist in any recognisable form. And when the site was no longer in use, it wasn't abandoned. It was deliberately buried, filled in with rubble and soil, as if the builders wanted to preserve it, to hide it, to ensure it would survive for some future generation to discover. Why bury your greatest architectural achievement unless you know something is coming, unless you're trying to preserve what you can before catastrophe arrives? In 1929, a Turkish naval officer named Piri Reis created a world map incorporating information from older sources, some dating back centuries. The Piri Reis map shows the coastline of Antarctica with remarkable accuracy, depicting bays and inlets that match the actual geography beneath the ice. But Antarctica wasn't officially discovered until 1820, and its coastline wasn't accurately mapped until the 1950s using seismic sounding equipment to see through the ice sheet. How does a 16th century map show Antarctic geography that was covered by ice for thousands of years? Piri Reis claimed he was copying from ancient maps, some from the time of Alexander the Great or earlier, sources now lost, but apparently preserving geographic knowledge from a period when Antarctica's coast was visible, before glaciation covered it. Mainstream academics dismiss the map's accuracy as coincidence or misinterpretation. But if you look at the coordinates and compare them to modern satellite data, the match is too close to ignore. Someone at some point mapped Antarctica when it wasn't fully glaciated, which means someone possessed the maritime technology and geographic knowledge to reach and chart the southern continent before written history begins, before the civilizations we recognise as advanced existed in any form we've documented. These are threads, not proof, fragments that might connect to form a picture, or might be coincidental anomalies misread by researchers too eager to find patterns in randomness. But when you sit with all of it together, when you hold the Sumerian tablets with their impossible mathematics, when you consider the global pattern of advanced knowledge appearing without precedent, when you factor in the geological evidence of catastrophe at exactly the period where mythologies place their floods and destructions, when you recognise that mathematical systems don't appear perfect and remain unchanged unless they're being preserved rather than developed, the threads start to pull tight. They begin to suggest not certainty, but possibility. The possibility that human civilization is older than we've acknowledged, that our history has been interrupted by catastrophe, that what we call the first civilizations might be the survivors, the inheritors, the ones who remembered enough to rebuild, but not enough to fully understand what they'd lost. The Sumerian scribes who copied Plimpton 322 weren't creating trigonometry. They were preserving it, maintaining a table whose original purpose they might not have fully grasped, ensuring the numbers survived because someone had taught them. These numbers mattered. These calculations were important. This knowledge must not be forgotten, even if the reasons why had faded into mythology about gods who descended from heaven and gave humanity the gift of measurement and mathematics. And maybe those gods were mythologized memories of teachers, real people with real knowledge from a real civilization that existed before the Ice Age ended, before the floods came, before the climate shifted and erased most traces of what had been, leaving only scattered survivors who carried what they could to the new world emerging from catastrophe. The Sumerians didn't invent mathematics. They inherited it. And the source of that inheritance wasn't divine intervention or alien visitors, or any explanation that requires abandoning what we know about human capability. It was human, achingly human, the desperate preservation of knowledge by people who knew their world was ending, teaching what they could to whoever would listen, hoping that somewhere, somehow, the mathematics would survive, even if the civilization that created it did not. Imagine being that teacher. You understand base 60 mathematics, can calculate square roots to multiple decimal places, can predict eclipses and track planetary cycles. But your cities are flooding, your institutions are collapsing, your libraries are burning, and the people you're trying to teach are struggling just to survive in a world where the climate has shifted, the food has disappeared, and everything familiar is dissolving into chaos. What do you save? What can you save? Maybe you press calculations into clay tablets, hoping they'll survive. Maybe you teach formulas to students who don't fully understand them, but memorize them faithfully. Maybe you encode knowledge into myths and stories, wrapping astronomical data in narrative frameworks that people will remember and retell, preserving the numbers even if the context is lost. And maybe, just maybe, those tablets and formulas and stories drift through the dark centuries after your civilization falls, carried by refugees and wanderers, until they reach people in Mesopotamia who are learning to farm and build and write. And those people receive your mathematics like a gift from heaven, like divine revelation, because to them it is miraculous. It is impossible. It is knowledge that lets them measure the world with precision they could never have developed on their own. So they copy it. They preserve it. They build their civilization on the foundation of your numbers, never knowing your name, never understanding where you came from, only knowing that the mathematics works, that the calculations are true, that the knowledge must be maintained. And 4,000 years later, archaeologists will find those tablets and wonder how such sophistication could appear with no precedent, never suspecting that the precedent was buried beneath 12,000 years of geological time, erased so completely that only the mathematics survived, an echo of a voice calling across the catastrophe, preserved by people who became the custodians of someone else's legacy, maintaining light they didn't kindle, carrying forward numbers that still work, still function, still let us measure time and space using a system created by hands whose names we'll never know. The clay doesn't forget. That's what makes these tablets different from every other artifact we've pulled from the ruins of lost civilizations. Stone crumbles, metal corrodes, papyrus burns to ash in seconds, but clay, when fired by heat or hardened by time, becomes nearly indestructible. The tablets that survived Sumer's collapse weren't preserved through careful curation or lucky accident. They survived because fire baked them harder, because floods couldn't dissolve them, because the very catastrophes meant to erase Sumerian civilization instead immortalized its mathematics, pressing those calculations into a medium that would outlast everything else, ensuring that whoever came after, whoever dug through the ruins, would find the numbers still waiting, still accurate, still functional after 4,000 years of burial. Maybe that's not accident. Maybe the Sumerian scribes understood what medium would survive longest, chose clay deliberately knowing that stone could be shattered and organic materials would decay, but fired clay tablets stacked in libraries would endure through almost anything short of complete geological burial. And maybe they learned that from whoever taught them the mathematics, from teachers who had already watched one civilization fall and understood what survives catastrophe and what doesn't. Who knew that knowledge encoded in durable materials and copied redundantly across multiple sites had the best chance of transmission across the dark periods when institutions collapse and learning stops and humanity has to rebuild from fragments? The tablets weren't just mathematical textbooks. They were time capsules, messages thrown forward across centuries, insurance against forgetting. In the basement of the British Museum, in the restricted archives where the oldest tablets rest in climate-controlled darkness, you can still see them if you're granted access. Plimpton 322 in its padded tray, the surface worn smooth in places where ancient fingers handled it, the cuneiform marks still sharp where the stylus pressed deep. BM 13901 with its 6 decimal place calculation of the square root of 2, the numbers marching in neat columns down the face of the tablet. AO 6484 from the Louvre's collection, photographed and catalogued but still mysterious, still whispering questions about pi and circles and granaries that needed precise volume calculations. Each tablet is cool to the touch, slightly rough, heavier than you'd expect for its size. And if you were allowed to examine them closely, if you could turn them in your hands the way the scribes once did, you'd see the same thing on many of them. Fingerprints, thumbprints pressed into the wet clay before it dried, preserved for millennia, the unique whorls and ridges of hands that belong to people whose names we'll never know, but whose touch remains, frozen in the medium they chose specifically because it would remember. Those people lived in a world we can barely imagine. No electricity, no computers, no symbolic algebra, or place value decimals. They calculated with reed styluses and wet clay, solving quadratic equations by manipulating physical tokens, tracking planetary movements with naked eye observations and institutional memory spanning generations. Yet they achieved mathematical precision we didn't match again until the Renaissance, solved problems we wouldn't formally systematize until the 19th century, encoded knowledge that still functions perfectly when we apply their methods to modern calculations. The sexagesimal system they used still measures every hour of our lives, still divides our circles, still provides the framework for navigation and astronomy and time itself. We never abandoned it because it works too well, because whoever designed it understood mathematics deeply enough to create something elegant and functional and perfect enough to last 5,000 years without improvement. Who are they? We've spent 5 parts of this story circling that question, examining the evidence, testing possibilities, following threads that lead into darkness. The tablets tell us the Sumerians possessed advanced mathematics with no developmental history. The global pattern tells us similar knowledge appeared in Egypt and India and Mesoamerica without clear sources. The geological record tells us catastrophic climate change struck at the end of the Ice Age, exactly when mythologies place their floods and destructions. The myths themselves from every culture speak of teachers and divine instructors and knowledge that came from before, from elsewhere, from sources the myths describe as gods but treat as historically present, walking among humans, establishing civilizations, then departing or disappearing. And the mathematics itself, precise and unchanging and carefully preserved across millennia, feels less like invention and more like inheritance, less like discovery and more like desperate salvage, knowledge carried across catastrophe by people who understood they were the last generation that remembered, who pressed what they knew into clay and taught it to whoever would learn, hoping that somewhere in the future someone would find those tablets and understand what they meant. Maybe we've been asking the wrong question. Not where did Sumerian mathematics come from, but why did it survive? What made it important enough that scribes copied the same tables for 1500 years without changing them, maintaining accuracy they might not have fully understood, treating these numbers as sacred, as untouchable, as truth that must be preserved even when the civilization that used them was collapsing under the weight of drought and invasion and the inevitable entropy that claims all human institutions eventually? The answer might be simpler than we want to admit. It survived because someone, somewhere, had decided it must. Because teachers from a lost world looked at students in the new world emerging from catastrophe and said, these numbers matter. These calculations let you measure reality, understand the sky, predict the seasons, build cities that won't collapse, maintain the knowledge that makes civilization possible, learn them, copy them, don't change them, pass them down exactly as we teach them. And those students became scribes, and those scribes became teachers, and the chain continued for 4,000 years, each generation maintaining what the previous generation had received. Custodians of mathematics they inherited from a source that had faded into mythology, but whose legacy remained undeniable in tablets that still worked, still calculated correctly, still unlocked the patterns woven into the structure of time and space. There's a beauty in that if you can let yourself see it. Not the triumphalist narrative of human progress we usually tell, where each generation builds higher than the last, where we stand at the apex of achievement looking down at primitive ancestors who knew so much less, but a different story, humbler and stranger, where knowledge moves through cycles, rising and falling, civilizations achieving great sophistication, then losing it to catastrophe, survivors carrying what they can forward, teaching fragments to new cultures who preserve those fragments faithfully even when they don't fully understand them, maintaining light through dark ages until eventually, gradually, understanding returns, and we recognize in the ancient tablets not primitive confusion but advanced mathematics we're only now sophisticated enough to appreciate. Maybe that's the real pattern of human history. Not linear progress, but cyclical preservation. Waves of knowledge that rise and crash and rise again. Each peak built on foundations laid by the previous cycle. Each valley crossed by people carrying seeds of learning that will bloom again when conditions allow. And maybe, if we're honest, we're not that different from the Sumerian scribes. We copy calculations we don't fully understand, use technologies whose fundamental principles remain mysterious to most of us, inherit systems built by people whose names we don't know and whose genius we take for granted because it's been so thoroughly incorporated into the fabric of our world that it's invisible. Every time you check the time, you're using Sumerian mathematics. Every time you navigate by coordinates, you're thinking in base 60. Every time you measure an angle or calculate a circle's circumference, you're applying methods developed by hands that left fingerprints in clay 4,000 years ago, methods they might have inherited from sources even older, methods that work so perfectly that we've never needed to replace them. We're still using their numbers, still maintaining their system, still, in our own way, custodians of knowledge whose origins have dissolved into time, carrying forward what works even when we've forgotten where it came from. At night, when the museum lights dim and the archives fall silent, I imagine those tablets breathing in the darkness, each one a message, each one a deliberate act of preservation, each one pressed into clay by someone who believed the knowledge mattered enough to survive them. They were right. The tablets outlasted Sumer. They outlasted Babylon and Assyria and every empire that rose and fell in Mesopotamia across 4 millennia. They survived fires and floods and the slow erosion of geological time. They waited in the earth until we developed the curiosity and technology to excavate them, the linguistic skills to translate them, the mathematical sophistication to recognize what they contained. And now they speak to us across the centuries, not in words but in numbers, not in narrative but in calculation, pure and precise and undeniable. The mathematics works. That's what survives every argument and skepticism and academic debate. When you apply their methods, you get correct answers. When you use their tables, you calculate accurately. When you follow their procedures, you solve problems that troubled mathematicians for thousands of years. The knowledge is real, functional, proven, and it came from somewhere. So what if Sumerian math came from an unknown source? What if the question isn't whether it did, but why we've resisted acknowledging it for so long? Why we've insisted on primitive origins for knowledge that shows no primitive stages? Why we've dismissed mythologies that might be preserving genuine historical memory simply because they describe events outside our established timelines? Maybe the problem isn't the evidence. Maybe it's our framework, our assumption that civilization began 5,000 years ago and everything before that was gradual progression from stone tools to agriculture to cities, neat and linear and comfortingly progressive. But what if it wasn't linear? What if human civilization is older, more complex, more interrupted than we've admitted. What if the Sumerians really were inheritors rather than inventors, preservers rather than pioneers, the ones who remembered just enough to rebuild, who received mathematics from teachers whose own civilization had fallen, who pressed that knowledge into clay because they understood they were links in a chain of transmission that stretched backward into darkness and forward into a future they'd never see, hoping that someday someone would find their tablets and understand. The desert wind still moves across the ruins of Uruk, carrying grains of ancient brick dust into the Iraqi sky. Beneath the sand, thousands more tablets wait, still unexcavated, still silent, each one potentially containing more impossibilities, more calculations that shouldn't exist, more evidence of knowledge that appeared too early and worked too well. And in the archives where the excavated tablets rest behind glass and security, they wait too, patient as only clay can be, holding their numbers, maintaining their precision, preserving their secrets. The fingerprints are still there if you look closely enough, pressed into the clay by hands that solved equations we're still teaching in schools, that calculated to decimal places we didn't achieve again for millennia, that understood the sky well enough to track planets and predict eclipses and measure time with accuracy that still governs how we divide our days. Those hands belong to people who knew something important, who believed that knowledge must survive, who chose the most durable medium they could find and pressed their understanding into it with care and precision, creating time capsules that would outlast everything else their civilization built. They succeeded. The knowledge survived. The question is whether we're ready to acknowledge what that survival means, whether we can accept that our history might be longer and stranger than we've allowed ourselves to imagine, whether we're willing to look at those ancient tablets and see not primitive beginnings, but sophisticated inheritance, not the first words of mathematics, but words carried forward from earlier voices, echoes of teachers calling across Catastrophe, preserved by scribes who became the custodians of someone else's genius, maintaining numbers that still work, still measure, still unlock the patterns hidden in time and space and circles, a legacy from an unknown source that shapes our world still, pressed into clay by people who understood what would survive and chose to save what mattered most. The mathematics, always the mathematics, perfect and patient and waiting for us to finally understand that sometimes the most advanced knowledge is the oldest, that sometimes the deepest wisdom comes from the furthest past, and that maybe, just maybe, we're not standing at the beginning of understanding, but somewhere in the middle of a much longer story, one that began before history and continues through us, carried forward by anyone willing to preserve what works even when we've forgotten where it came from. The tablets remember, the clay doesn't forget, and the numbers, those impossible perfect numbers, still whisper the same truth they've held for 4,000 years. Someone taught us, someone knew, and their mathematics survives.